Hello, hello. So welcome to MA 174.1, our first asynchronous session, which is unfortunate. Unfortunately, I also do not have my good microphone, so you might have to um, suffer through bad audio quality. So I think you might be able to hear my mouse clicks here and there, but let's bear with it because for next meeting we'll be moving to the pump performance experiment. So I think we have to finish this discussion before we go ahead with that experiment. All right. So let's go. So what will we be covering for today? So first and foremost, we will look at how to examine the performance of a pump, particularly a rotor dynamic or non-positive displacement pump, and how do we select them? So what's inside the catalog just in case you get into procurement, and what should be the parameters that you should look out for? Next is what happens when pumps are connected together. So first and foremost, let's go ahead with pump selection. So if you recall, there are two types of pumps. You have the positive displacement pump and you have your rotor dynamic pumps. So with rotor dynamic pumps, they are able to provide this flexibility in flow rate, and you'll see that here. So we have to look at two curves when we're examining pump performance. The first one, what you see here in blue, this is the discharge head that the pump can provide depending on the flow rate. And you can also look at it vice versa. This is the flow rate that the pump can generate given a particular discharge head. We call that the pump performance curve or the pump curve. Now, the red curve that you see in this graph currently is the required head for a particular system. So this depends on the application requires. So why is it growing with respect to flow rate? That is because the friction head steadily increases as you increase the fluid velocity. This is what we call the system curve. And of course, you can see it in the graph as well. There is a point wherein the pump can provide exactly what the system needs at a particular flow rate. And we call this the operating point of the said system. Now, you may want to ask, okay, so where do these curves come from? So for the pump performance curve, this would be the burden of the supplier or the distributor. It is the manufacturer's job to adequately describe what the pump that is selling can do. Now, when it comes to the system curve, this is the burden of the client. This is up to you, the procurement officer or the design engineer, to establish the range of requirements for your system. And the easiest way to do this is, of course, with the Bernoulli's equation. Now, aside from the discharge head per flow rate, there are other curves that we can look out for. So when it comes to pump curves also, to make sure that we're not getting scammed or anything, we actually have regulating bodies that standardize particular tests on pumps and other devices such that you have this confidence that if this supplier has been certified by so and so regulating body, then that means what they are showing you is, for the most part, legitimate. So actually, our experiment is based on the standardized test that one of these regulating bodies have mandated. Now, aside from the head, the discharge head curve, you also have curves for efficiency and curves for power consumption. That is the green dashed line in this curve, and the power curve is the red dashed line. So in particular, with the efficiency curve, you'll see a peak in the curve. This peak is what we call the best efficiency point, or the BEP. So the BEP tends to be, or at least it is not burdened to be similar to the operating point. So again, the operating point and the best efficiency point may or may not be the same. So you might ask, okay, so if I am designing my system, which point on the available head or the system curve should I prioritize? And I think that's a good question for everyone to digest. So I'm gonna leave it to you to mull over or research. Now, all of these curves pertain to the more on the performance side of the pump, but there is also this danger, especially in the suction side, wherein the pressure can get way too low, such that the fluid starts to vaporize and cavitate all over the impeller. So, in order to avoid cavitation, engineers specify what we call the net positive suction head. So, this is the suction head that you have to stay above of in order to avoid any bubbles from ruining your pump's performance. So, just like the pump performance curve and the system curve, there are two types of NPSH. First of all, you have the calculated NPSH. So this is the curve that can be generated based on your system characteristics. So here you have the suction head of your system subtracted by the vapor pressure head of your fluid. So since you have a velocity head here, of course, your NPSH calculated will differ at each and every flow rate. And there's a second one that is supplied by the manufacturer. This is called the required NPSH. So you cannot calculate this using your system. This is run by tests done by the manufacturer as per standards enforced by institutions or um, standard makers. So in the next graph, you will see here the two curves. So the solid purple line that you see here is the calculated NPSH of your system, and the dashed line is the NPSH for the pump. Now, as long as the calculated NPSH stays above the record NPSH, your pump should probably be safe from cavitation. However, if you operate too far with an increased flow rate, you might see that the required NPSH will exceed what the system can supply essentially. And that will be a zone wherein your pump could be damaged because of cavitation. So next, let us now look at pump selection. So, okay, so I have the gist of things. I know about the pump performance curve. I know about the efficiency curve. I know about the power curve. I know about NPSH. What would the catalogs for pumps actually look like? So, for example, let's say you're in procurement or you're in design and you're looking at different catalogs from different suppliers. What you might expect, especially for rotor dynamic pumps, is that there are two key aspects of the catalog. First is what we call the selection chart, and next is the specification table. So the specification table contains parameters relating to pump performance and other peripherals, such as the sizing of the suction, the discharge, as well as other things the supplier might want to specify for each model. Now, the selection chart, as you see here, they closely match the pump performance curve, but this time there's a whole lot of them. So each of these curves is the pump curve for a particular model. And if you want to find out which one, just look at the identifying number and then look for it in the reference column of the specification table. So let's say, for example, we're interested in GEJ 656 M4ME 1.5 for one reason or another. Maybe you just like the size of the motor or something. So in order to find that, let's just look for the reference number, which is 10, and we highlight the pump performance curve identified with that number. So here we go. Now, if we look at the endpoints, these are the endpoints of our pump curve for pump number 10. So you might want to ask, why is there a shaded area underneath the curve? And why does the shaded area not extend downwards to, let's say, free delivery? So that is actually a good question, and I think that would be a nice thing to mull over um, as you try to understand or grapple with pump selection. So what you'd also notice here is that the curves that are available to us is only relating to discharge per flow rate. If the supplier is meticulous, they could also supply the curves for constant efficiency and the power curves, the expected power consumption, depending on the discharge of your pump. Now, this is a little bit more chaotic. So what you notice here is that you have blue colored curves. So each of these curves are actually for different impeller sizes. So you have your 12.75 inch as the larger performance curve and 6.75-inch impeller has having the lower performance curve or the smaller one. So the green lines here are lines of constant efficiency and the red dashed line is for power. Now you might also see the required NPSH here above. This is not operating on the same scale as the performance curves. It has its own y-axis here. Now, for the reason why the head is a bit more important, I am not quite sure why the head is the most supremely important. However, when it comes to pump selection, um, you might prioritize the head over the efficiency of your system. So I'm not sure if this is reflected in your ME thermodynamics, but normally when you are given a Rankine system problem, the efficiency of the turbine is around 80% above. But when you are given a particular efficiency of the pump, it's usually 80 below. It never breaches 90 or 85 ever. So you might kind of see that for pumps at least, the discharge head is more important than the efficiency. But of course, you are the client, so you might have different priorities other than the standard. So here, so the curve here is actually from Sengel, one of the references. This one is essentially the same concept, but in a catalog that you can easily find on the internet. So this catalog actually supplies pumps in different impeller sizes. So it's just like the previous curve wherein you have these descending slopes and each descending slope has a identifying letter identifying the impeller diameter. And you also have lines of constant efficiency. So for pumps of a particular size, especially motor-driven pumps, the motors, if they consume AC, they usually only operate on one speed. However, you do see variable speed motors, and when you do see variable speed motors, instead of differing impeller sizes, you have differing impeller speeds specified. So if you see here in the column, you have a particular speed defined, and they tested for the pump performance along that particular speed. So can we actually go between these speeds? I think it depends on the control level of speed control that you have for each pump. I believe you can go in between these speeds. However, you may just have to interpolate the performance of your pump along the way. So, all right. Those are the catalogs that we've seen. Next, we go to the pump performance setup for experiment one. So this is a crude drawing of what the pump location looks like. So if you've been in the garage of Amtech before, especially for the engine performance test, you've probably seen this to the left of the entrance to the garage. So in the suction side, you don't have a lot. Basically, you only have a valve and a gauge. However, for the discharge side, you have several equipment. You have several instruments, and you have uh, several means of several tools by which you can control the flow rate. Now, there used to be a test for net positive suction head in the standards. I think the engineer for next meeting will ask about that. However, the revised version no longer has the NPSH test. So we'll only be doing pump performance test. Essentially, the discharge head depending on the flow rate that can be supplied. So in the experiment, we'll be generating three curves in particular: the pump curve, which is the available head curve, the power curve, and the efficiency curve. And we'll be plotting that alongside the pump speed, since the pump set that we'll be using will probably be an engine powered pump. So now let's see towards the calculation. So the pump head, the available head that they can supply, is the difference between the discharge and the suction head. So each of these heads is composed of differing heads. So we have the pressure head, the velocity head, the elevation head, and the losses, of course. So these losses include the friction head and the minor losses along the system. So during the experiment, I'll have you take note of the lengths of the pipes as well as the different attachments and the minor losses connected to those. So now this is how you calculate the pump curve. For the efficiency, we will use the classic equation for pump power, which is gamma QH. And for the input power, now this is the one that we've had the most contention over. So there are several ways to calculate for the input power. I believe we can rely on the brake specific fuel consumption because you'll be measuring the flow rate of the fuel during the performance test. The brake specific fuel consumption, if you recall from your engine's performance test, this is also a curve. However, what we'll be doing is that the engine is at full throttle at all points of the experiment. So that means even though this is a curve, we should see a constant BSFC for which we can connect to the flow rate of the fuel in order to calculate the power that is being fed to the pump set. Now, if this is not possible, like if you cannot find the specific fuel consumption of the specific pump, you might have to use the heating value of the pump. If heating value, I believe you just have to rely on the lower heating value of the fuel. So please, during the experiment, you might want to inquire of the test engineer what the brake specific fuel consumption at full throttle is, or the specific fuel that they're using so that you can at least have an estimate of the lower heating value. For the NPSH, no, we will not be doing that test. So yeah. So in case you have any questions, just forward it to as a comment, whether public or private. I would prefer a public comment so that other students may benefit from your question. So now we'll be looking at pumps in networks. So this one is easy, although when you look at the curves, they might be a little bit more confusing. So there are two kinds of networks. There is a series network and a parallel network. The series network is not all too common. Typically, when you want pumps in series, you just use pumps with multiple stages. So here, as you can see in the images, you have the rare instance of centrifugal pumps being connected in series, and they tend to be in unusual configurations. I believe that is why we don't see pumps in series overall. Now, when you connect them in series, what happens is that the flow rate does not change. However, the available head increases. It stacks vertically. So when you have the pump curves of, let's say, uh, three different pumps, so here in this image, you have pump 1's curve, you have pump 2's curve, and you have pump 3's curve. If you stack them in series, their curves actually increase vertically. They can provide a larger discharge head overall. So this is what the curve looks like. So now, what you notice here is that the combined curve, which is in series, is split into three zones. If we look down here at the individual pump curves, there are points wherein the smallest pump reaches what we call free delivery, essentially free flowing fluid with no discharge head. So this is reached early by pump 1 and then by pump 2. Whenever the flow rate reaches or exceeds the free delivery of one of the pumps, it is better to shut off that particular pump instead of continuing. So you see here in the first zone, you have all pumps active, and once you reach free delivery with pump 1, it's better to shut off pump 1 and just stick with pumps 2 and 3. And eventually, you might not need the series network. So if you have a high flow rate demand, you might just buy a more powerful pump, or you can just buy the identical pump in order to stack it, essentially stack the head better. So this is actually not a common setup. So normally, if you're in the industry, when you are networking pumps in a single series or in a parallel network, you use identical pumps. So single here is being meticulous, wherein you might just encounter a particular configuration, especially if you're not the one to who designed the network. You might just see, oh, these are differently sized pumps. This is how the curves interact when they are in series. Now, for the more common arrangement, uh, for parallel networks, the flow rate is actually increased when you stack them in parallel. So this is the more common arrangement again. So this is how you usually see pumps in networks. So they are connected to the same suction, and their discharge is essentially in the same connection as well. So what happens here is, unlike the series configuration, the combined curve does not stack vertically. Instead, it bulges out horizontally, such as here in this case. So when you use pumps in parallel, your priority is the flow rate. So you might have several weak pumps, like for pumps 1, 2, and 3. And for one reason or another, you found that stacking pumps in parallel is more economical for you than having one giant pump managing that flow rate. So Sengal again is being meticulous. It has three pumps of differing stages. So these pumps also have differing free deliveries and also differing maximum discharge heads. So for pumps in parallel, what you are looking out for is the smaller pumps discharge head limit. So essentially, the top of this curve is where the pump uh, can no longer provide flow above this particular head. So I think this is a little more dangerous. So if the required discharge head exceeds the maximum discharge head of one of the pumps, you have to shut off that pump, etc. So this is kind of the reverse problem. So if you require a high discharge level, it's better to just connect them in series or just buy a bigger pump. However, if flow rate is your priority, instead of buying a bigger pump, I think you can just stack pumps in parallel. So that is that. So I'll be recording a separate um, video for the examples. And until then, stay safe and thank you so much.